Our goal for today is to talk about a way of solving for the particular solution in a more generic case. So if you watched the video from last time, we talked about the method of undetermined coefficients, but it was very narrow. Essentially, it relied on everything looking and behaving like constant coefficients, linear differential equations, and that constant coefficient really restricts the kind of things we can do. So we're going to talk about a different idea today called variation of parameters and work through how it works and derive the formula for it. But before we get to that, a quick callback. Cramer's rule. Now, Cramer's rule is a shortcut way of solving a system of equations by use of determinants. And what Cramer's rule does in the background is it really works through the process of elimination and just says, oh, this is what it turns out to be equivalent to. And so how does it work? Well, suppose you have a system of equations and we have coefficients, so think of these a's as our coefficients. The x's are what we're trying to solve for, and the b's are what we're aiming for. Now, one of the things that we learn, especially if we take linear algebra, is that we can write this in sort of a shorthand notation, which is to say we group our coefficients into an array which we call a matrix. We have our list of unknowns, which we put in a column. We call this a vector. And we have our target, what we're trying to achieve. Now, what does Cramer's rule state? Well, Cramer's rule says, hey, if you want to solve for x, here's what you do. You take a ratio. And we're solving for x1. Downstairs, take the determinant of this matrix. Upstairs, take the determinant, but now take your matrix and replace the x1 column, so this is the column attached to the x1s, by the b's. In a similar way, for x2, it's this, again, downstairs determinant of a, upstairs the determinant, but take a and modify it by making the x2 column, you see how these are attached to the x2s? Replace that by the b's. And you solve, and you'll get the right answer. Now, there's something it says there at the bottom which says the similarity holds in general. And there's two key things that it does. In general, you can say, oh, it works for any number of equations. So 3 equations, 3 unknowns, 4 equations, 4 unknowns, so forth and so on, as long as we're talking about linear equations. That's one way it generalizes. On a side note, we're only going to talk about 2 equations, 2 unknowns, because we're just limiting ourselves to second order in our discussion today. But there's another way it generalizes, which is to say, we oftentimes think about solving things as like, oh, we're looking for numbers. But there's other things besides numbers we might want to look for. And in our case, we're going to be looking for functions. Does the same work, does the same rule still work? In other words, does Cramer's rule work if it's not just numbers? And the answer is yes. Cramer's rule still works. In general, you just say, well, what does the machinery ask? It asks to be able to multiply and to add. And as long as we can do those things, then we can do whatever we want. And since we can multiply functions and we can add functions, it also works for functions. All right, now on to the main event. So now let's talk about what's going on, variation of parameters. It's going to take a while for us to get to the formula. So this is the start of it. We won't get it all done in one slide, so be patient. So we're starting with the following. We have a second order linear non-homogeneous differential equation. But we are going to be more general. So in other words, these can be functions of x, and we're not going to make any assumption about f of x, other than to say it's a function. It doesn't have to be a nice function. It could be a rather unusual, strange function. And so that's why this is a more general form compared to what we talked about last time, which says, well, you have to have constant coefficients, and you have to have nice. None of that, none of that. So it's more powerful. But of course, with great power comes a lot more steps and a little bit more work involved. So where are we at? Well, we're going to have 2 solutions, y1 and y2. So we're really saying, hey, y1 and y2 form our y sub c, which is to say that yc is some constant y1 plus some constant y2, where these constants here are numbers. Now, what we're going to do is we're going to say, well, let's find a y sub p. And it works by saying, okay, start with what we know. We have our y1, y2, so we want to somehow use y1 and y2 to help us find our yp. And that seems wrong because you say, well, wait, when we plug in y1 or y2, out comes 0. How can we use that? Okay, so here's how we do it. We're going to set y sub p equal to u1 y sub 1, u2 y sub 2. And we're going to say this holds. That's our first assumption. Now your first instinct is to say, wait, you just said that. But there's something slightly different here. These a and b, these here are constants. We said that, right? These u1, u2, these are functions. So they're not numbers, they're actual, goodness to gracious functions. You know, they're unknown functions. And so okay, so that's the difference. Now we say, all right, we've made an assumption. By the way, how many assumptions are we going to get? We're going to get 2 assumptions. Y2, well, we have 2 things that we've introduced. So we have 2 knobs that we can play with. And so we say, well, one of our assumptions says that, okay, it's a solution. Well, okay, that puts a restriction on. And then if we make a second assumption, it's like, oh, now we can't fiddle anymore. It tells us we've reached our limit. Okay, so let's think about our second assumption. And our goal is to make things simple. So we know that this is a particular solution. So looking ahead, we're going to plug this in. Well, that says we need to find y prime and y double prime. So we say, all right, take the derivative. And when we take the derivative, we're going to do product rule. So the derivative of the first, u1 prime times the second, y1, plus the first, u1, times the derivative of the second, y1 prime. So these 2 are the derivative of the first. In a similar way, these 2, derivative of the second. Now, we said we get a second assumption. So we pull it out at this stage and say, okay, let's have our second assumption be that together, these are 0. So we can make that. We're allowed. We're allowed to add assumptions. But now we've used up our assumptions, and we have to see what goes for the rest. All right, so since that's 0, we say it's gone. We don't have to worry about it anymore. So we cross it out. And now we have u1, y1 prime, take the derivative, u1 prime, y1 prime, and then plus u1, y1 double prime. Here, u2 prime, y2 prime, plus u2, y2 double prime. So that's our second derivative. We can't make any more assumptions, so we say, okay, that is what it is. Now, we know that this is a solution. Y sub p is a solution, which means that when we plug it into our differential equation, out comes f of x. So we have that f of x is our yp double prime plus px y sub p prime plus qx y sub p. And we start gathering. Now, where do we get pieces from? Well, we have our yp double prime as this part, and so that comes from there. All right, so that's, pay attention. And now, what are we going to do? Well, let's see what else we have. We have for u1, well, we have our y1 double prime. That's coming from here. And then we have our p of x, y1 prime, and that's coming from here. And then we have our q of x, y1, and that's coming from there. All right, so these pieces are coming from our yp double prime, our yp prime, and our y sub p in a similar way. And essentially in the same way, this y2 double prime comes from there, this y2 prime from there, and this y2 from there. And notice all these have a u2, so you pull it out. All right, well, what's nice? You can already see what it says. This part is 0 because it's a solution of the homogeneous part. Okay, great. And that part is 0 because it's a solution of the homogeneous part. Wonderful. So what does that tell us? Well, it tells us that actually f of x is really very simple. And so we have the following two assumptions. We have this piece here, namely that u1 prime, I'll write as y1 u1 prime plus y2 u2 prime is equal to 0. That's this assumption. And we have that our y1 prime u1 prime plus y2 prime u2 prime is f of x. And you might say, oh, this is something that he keeps talking about all the time. Two equations and two unknowns. Well, of course we see the two equations. What are the two unknowns? And that's the key here, is our two unknowns are u1 prime and u2 prime. We already know about y1, y2. We already know about 0. We've known 0 for a long time. And we know about f of x. What we don't know are those two. But two equations, two unknowns, we have a real chance. So writing it down again, here are two equations. In matrix form, well, we can say our coefficients are these functions for y and their derivatives, y1, y2, y1 prime, y2 prime. And then our unknowns, u1 prime, u2 prime, 0, f. All right, well, Cramer's rule. There's a reason we talked about it. It's because we would get to this point. And we say, all right, by Cramer's rule, if I want the u1 prime, I'm going to replace the first column by this piece here, 0f, y2, y2 prime, and I take the determinant. Well, 0, subtract, and that's minus y2f. Now downstairs, we've seen this determinant before. It's the Wronskian. Remember how the Wronskian worked? The first row was the function, the second row was the derivatives, and you took the determinant. So that w is for the Wronskian. And so, cool. See, there was a reason that we talked about it. It was going to come into play at some point in time. All right. Now, in a similar way, for u2 prime, okay, you replace the second column by 0f. Now, the determinant, y1 times f, and then you have a 0. Again, Wronskian. So, we now know, solving this system of equations, we get u1 prime, u2 prime. How do we get u1 and u2? Well, the answer is you integrate. So our great aha, u1 is the integral of minus y2f over the Wronskian of y1, y2 dx, and u2 is the integral of y1f over the Wronskian y1, y2. All right, and we're done, right? Because what was our assumption? Our assumption was that our solution looked like u1 times y1 plus u2 times y2. Well, we found u1 and u2. So, putting it all together, we have the following. If we have a differential equation, second order, so there is a similar formula for third order, for fourth order, and so forth and so on, but of course, the ideas are similar, the complexity grows. So we're not going to worry about that. Our point right now, our purpose is, let's get a handle on at least second order. Because we're not going to be able to do higher until we understand. And to get to higher, you need to spend a little bit more time in your linear algebra, which is a wonderful place to spend time in, by the way. All right, so for our second order differential equation, of the form y double prime plus p of x y prime plus q of xy equals f of x, where y1 and y2 are linearly independent solutions to the corresponding homogeneous ODE. So in other words, they're the y sub c. We want them to be linearly independent, because we're going to use the Wronskian. Then we have that y is minus y1 integral y2f over the Wronskian y1 y2 dx plus y2 integral y1f over Wronskian y1 y2 dx. And at this point, like, wait, what? But it's not that bad, right? Because what do you see? u1. So this is essentially, add the minus, that's our u1, that's our u2, so it's u1, y1, u2, y2. So it's finding those things. Now, don't panic about the formula. At this stage, if we ask you a problem about variation of parameters, we will give you the formula, because it's not the easiest formula to derive, it's not the worst formula, and there's sort of a process. What we want to do is make sure you understand how to use it. There's one important thing I want to point out right now, which is for this to work, you need to make sure that you have a 1 there. If you don't have a 1, the formula won't work. So what do you do if it's not a 1? Well, the answer is make it a 1. And how can you make it a 1? You divide through. That's what you do. Now, dividing won't actually change the y1, y2. It might change your f of x, but see how f shows up in the formula? So yeah, it's important that it gets represented there. So, all right, well, that's the idea. So this is a more generic formula than the method of undetermined coefficients. However, that being said, if you have a second order differential equation where method of undetermined coefficients works, then method of variation of parameters also works. So they're both equally valid. If they're both equally valid, should you pick one over the other, I would strongly encourage you to go for undetermined coefficients. You'll get the same answer, but the nice thing about undetermined coefficients is it's all algebraic machinery. And people tend to do a little bit better with algebra because they're more comfortable there. Whereas when you go with your variation of parameters, you start getting into integrals, and you might have to do integration by parts, and it can start getting messy, especially if you have things where you have powers of x and an exponential, and maybe even a trig function involved. So be good to yourself. We love ourselves, and we love ourselves enough to say, let's make it something that we're comfortable doing. So we've talked about the machinery. Now, let's work through an example. So here we go. Find the general solution for y double prime minus 2y prime plus y is equal to e to the t over 1 plus t squared. All right, comments to begin with. First off, we see constant coefficients on the left. We see e to the t on the right, and maybe we're like, oh, could we go undetermined coefficients here? No, not an option. But why not? Well, the reason it's not an option is this 1 plus t squared in the denominator. That's not something that comes out of a constant coefficient homogeneous differential equation. So undetermined coefficients, useless. Can't do it. So it's good to have other methods because, you know, as nice as one method is, it may not apply in all cases. All right, so we're going to do variation of parameters. So the good news is we have a formula. The nicer news for us is they wrote it down for us. Now you might notice something here. Here you see t's, but the generic formula has x's. So what do? Well, the answer is you adjust, right? You say, look, symbols can be changed. So now we say, really, it's just a function of t. So don't get too hung up on like, oh, it's got to be a function of x or it's not going to work. Here it's functions of t. No problems, no problems. All right, well, where do you begin? You always start by doing the complementary solution first. Always the first step. You have to have the y1, you have to have the y2, you have to have that Wronskian. You need all of these things. So let's begin by saying yc, well, y double prime minus 2y prime plus y equals 0, right? Because complementary says send the right-hand side to 0. Turn it into algebra. R squared minus 2r plus 1 equals 0, which becomes r minus 1 squared equals 0. Aha! R is a repeated root. 1. Well, repeated roots says our complementary solution looks like some constant and then e to the first root, so t, plus, well, it would be e to the t again, but we've already had that, so it's going to be bt e to the t. All right, so there's our yc. Good. Progress. And now we have to pick which one of these is y1 and which is y2. In the end, it doesn't matter. It won't make any difference at all. So let's make an arbitrary choice. Well, if we're going to make an arbitrary choice, we'll pick y1 to be e to the t, and y2 is t e to the t. And once you've made this choice, just stick with it all the way through. So we now know the y1 and the y2. That's good. So after your complementary solution, after you've picked which y1 and y2, now the Wronskian. All right, so here we go. The Wronskian of y1, y2. So that's going to be the determinant. All right, you write the functions down in the first row, and now write down their derivatives. Well, the derivative of e to the t is e to the t. Derivative of t e to the t, well, that's derivative of the first, 1 times e to the t, plus t times the derivative of e to the t, which is e to the t. All right, well, okay. Take your diagonals, because when you're taking the determinant, you have your two diagonals. So you go downhill, and you go uphill, and one you add, one you subtract. You just have to remember which is which. So this becomes e to the t times e to the t plus t e to the t, subtract, and then in the other direction we have e to the t times t e to the t. Well, that's e to the 2t plus t e to the 2t, subtract t e to the 2t, and you'll notice things simplify. And generically speaking, a problem that you get asked, the Wronskian should be pretty nice. The reason is because it's downstairs. You don't want a messy Wronskian. A messy Wronskian is trouble. Trouble, my friends. But not for us. All right. Good. So, we have our Wronskian. All right. Now, at the next stage, we want to go through and carry out these integrals. We can do them separately, and I think that's a good way to approach it. At least I'm going to do it that way. And so you can do it all in one line, but I like to sort of break things up just so I can take my time. Savor the math. Okay, so integral y to f over the Wronskian y1, y2 dt. What will this be? Well, we know what y2 is, so that will be t e to the t. We know what f is, so that's going to be an e to the t over 1 plus t squared. All right, so there's our y2, here's our f, and now our Wronskian is downstairs, and it's e to the 2t. So I can write that as 1 over e to the 2t. All right, so we have our pieces, right? y2, f, Wronskian downstairs. Now, I hope something simplifies. And it does. Well, what simplifies? The e's. You have e to the t, that's e to the 2t upstairs. You also have e to the 2t downstairs. Noise! So, this is the integral of t over 1 plus t squared. Now, this is the kind of integral that we've seen before. In fact, we often see this integral, And well, what do? In this case, what you can do is the following. You say, well, 1 plus t squared, the derivative of that is 2t. Well, we have a t, so we put a 2. But we'll put also a half to compensate for the 2. And now we have, function downstairs, derivative upstairs. And we say, oh, well, isn't that nice? That's a log. So that becomes a 1/2 natural log of 1 plus t squared. And then I'll put plus some constant, all right, c. Okay, so there's our first integral. Now, our next integral. Okay, here we go. We're going to integrate y1f over Wronskian y1, y2 dt. Okay, so y1, e to the t. Our f is e to the t over 1 plus t squared. So we'll go ahead and we'll just make sure we understand that. So we'll circle that. And so, okay, so that's, oh, let me get my page back. So that's an e to the t over 1 plus t squared. We have our Wronskian downstairs. So 1 over e to the 2t dt. And, again, the exponential functions cancel. Nice. So what do we have? Well, we have, this is the integral, 1 over 1 plus t squared dt. A favorite, fan favorite, this is perhaps the most popular integral. It's arctangent. Great. So, we are now ready to put it all together. It's actually going to fit on the page. That's crazy. That's crazy. Sometimes these are like 2-page problems, but I think this one we're going to fit on the page. All right. Okay, what's a good color to celebrate this? We'll go with this greenish color here. So we just put it together. So we have that y is equal to minus y1. Okay, so that's minus e to the t times 1/2 natural log 1 plus t squared plus c. And then plus y2. So y2 is t e to the t. So plus t e to the t times arctangent of t plus d. Now, if we expanded this, because why not? We could. We would have the following. We would have minus 1/2 e to the t log of 1 plus t squared plus t e to the t arctangent of t plus, here I have a constant times e to the t. The minus I can just absorb into the constant. So constant e to the t. And again I have constant t e to the t. And now you might say, oh, hey, wait a second. What do you have? This end part, this end part here is our yc. And the rest of this is our yp. And so we say, we have, in fact, the whole general solution. So I guess we'll add a side note here. So our side note is, if you include constants for your integrals, you'll get yp plus yc. No constants for your integrals, you're going to get just the particular solution. And why do you get the yc? Well, because you have first function times arbitrary constant, second function times arbitrary constant. And there we go. All right, we fit it on a page. These are quite a workout, but you just have to know the formula and carefully work it through. And the good news is, we'll give you the formula. So it's mostly about carefully working it through. So to recap, let's talk about the steps. We have time. Let's review. Find the complementary solution. That gives you y1, y2. F is automatically given to you. After you have your complementary solution, arbitrarily pick a y1 and y2. It's not like there's a right choice and a wrong choice. It's just there's a choice. You make a choice, and you live with it. After you've gotten y1, y2, do the Wronskian, because that's important. It shows up downstairs. And when I say stick with it, you stick with it. From that point on, everything stays y1, y2, because plus minuses matter. All right, so you work out the Wronskian. So now you have y1, your y2, your f, and the Wronskian. You compute the integrals. And the integrals, they may have to do a little bit of work. It depends, but they will be doable. You can do them. And after you do the integrals, you put it all together, and life is good. Life is wonderful. And with that, we'll see you again. Bye.